which is right there. What do we call changing? Well, okay, so this is where we left our physics heroes, with changing and instantaneous velocity. We said if you're in a car and you're traveling, what in the car shows you your instantaneous velocity? Speedometer. How easy is it to maintain exactly constant velocity? It's fairly challenging. That's why we have cruise control. You know, people tend to fluctuate a little bit. It's okay. But if we want average velocity, we can do that start to finish. For changing, we can only look at a point and we can look at a tangent line. Now, what do we call it when velocity is changing? You've heard this word. Acceleration. Yeah. And now we're going to start to talk about acceleration.
Do you know what year it is?
What year it is?
Yeah.
2017?
You're at 2019.
Just for the record, for anybody who has to watch these notes as catch up, we did not time travel, as much fun as that would be. I do not have a TARDIS. That would be awesome. It is 2017. Okay, so we're now going to talk about acceleration, not into the future. Acceleration is the rate of change in velocity. Okay, so acceleration is the rate of change in velocity over some given time interval. This is the next equation that you're going to want to put on that note card. And here we're talking about average acceleration. Okay, average acceleration is equal to delta v over delta t. Final velocity minus initial velocity over final time, initial time, Gesundheit. That said, we hardly ever deal with the actual times, like at second 1 and at second 15. We usually just give the interval. Over 14 seconds, over 37 seconds, over 2.5 hours, 2.5 hours, whatever. Acceleration can be negative or positive. Be really careful about the word deceleration. In common parlance, we use the word deceleration to mean what? Slowing down, hit the brakes, decelerate, decelerate. That's fine in everyday speech. It becomes a little bit less meaningful in physics because we can have negative acceleration, positive acceleration. As long as our direction of travel is positive, negative acceleration is slowing down. As long as our direction of travel is positive, positive acceleration is speeding up. If our direction of travel is negative, those things get flipped on their head, which is why the word deceleration is pretty meaningless. Acceleration has both direction and magnitude. It is a vector quantity. It's meaningless without the direction. It's meaningless without a heading, some sort of direction on it. So whether that direction is forward, backward, north, south, east, west, we do sometimes use sign as a proxy for direction, and that's fine. Acceleration is a vector. If you look in your Holt physics on page 49, we're going to walk through sample problem 2b together, and then all the 2b practice problems will be assigned. The bus slows down to a stop with an average acceleration of negative 1.8 meters per second squared. How long does it take the bus to slow from 9.0 meters per second to 0.0 meters per second? Okay, I keep saying it. I actually mean it. I will beat you with the physics stick over it. Write down your darn equation. Write down your base equation. In this case, A average equals delta V over delta T. In this case, because we're using this variant, you can also write A average equals VF minus VI over delta T. It's really helpful if you circle the thing you're solving for. And I can tell you that though this is like simple, stupid algebra, like simple, stupid, this is the most common algebraic mistake made by really smart people. When you're solving for something in the denominator, there's a common mistake people want to make. I still make it, and I've been doing algebra longer than you've been alive. So I go the long way around the barn so I don't make that mistake, which is I move that delta t over. It's a simple thing, but it prevents making a common dumb mistake. People end up solving for the reciprocal of time rather than time itself. All right. I'm telling you, I've made every dumb mistake you can make, so I'm uniquely qualified to help you avoid them. Okay, so now we have our rearrangement, and on a test, I'm also going to tell you that this is worth a point, that's worth a point. showing the base equation, showing how you rearranged it. Yes, I am beating you with a stick to force you to show your logic on paper because I will pay you for your logic in points. All right, now, also things I'm going to pay you for. I am going to pay you to list your variables. Seems simple. Many years ago, I had a young man, he was a bright young man, he was a very smart young man, who had always gotten math totally naturally. He didn't have to show his steps, he didn't have to write anything down, it was just all easy for him. And science had been easy for him, and he hit a little bit of a stumble the first unit of physics. And we sat down and we walked through some stuff, and I preached the gospel of writing down your equation, showing your rearrangement, writing your variables. And he had very little impulse control. So in the middle of the Chapter 2 physics test, he suddenly screams, "Oh my gosh, Moser! Physics is so easy when I write stuff down!" Thank you. Yes, it is. Shut up and take your test. It is. It's really easy if you just use a process and a pattern and write things down. So we're going to list our variables. The acceleration is given as negative 1.8 meters per second squared. The final velocity is given as 0.0 meters per second. And the initial velocity is given as 9.0 meters per second. This couldn't be a whole lot easier. Let's plug in. And let's do a little bit of very quick dimensional analysis on this. I probably should have done it in the last step, but hey, I didn't. So I have delta t, which we would like to end up with seconds. And I have meters per second minus meters per second divided by meters per second squared. Off to the side, I know meters per second minus meters per second is going to give me meters per second. That's divided by meters per second squared. Here's where I saw a very common mistake on the dimensional analysis questions on the test. When you do this, and I'm telling you this because I make this stupid mistake, actually show the inversion and multiplication because it's a really common mistake. Like 8 out of 10 people make this mistake. So I literally show that for myself. Oh yeah, meters cancel. I'm left with seconds. That's what I want. So there's my dimensional analysis piece. That is the most common mistake. Okay, calculator answer. Okay, I get a delta t of 5 seconds. Is that the correct recorded answer? That's my raw answer. That's what the calculator told me. Is there anything I need to do to that before I record it? I need to add a 0.0 because I have 2 sig figs in this problem, and I need to make sure that my answer reflects that. So my raw answer, usually we're trimming on the raw answer. This time, we're actually adding something to get our sig figs. So the raw answer is that the time is 5.0 seconds. Okay? These are easy. Enjoy them. You've got a little bit of time to work on the practice problems 2B on page 49. So that is 2B, page 49, numbers 1 through 5. And I'll give you probably 20 minutes or so to at least get a head start on those. You can always check your answers. You can take a picture of the answers. And then we'll continue on because I want to talk about graphical interpretations of acceleration. And talk about graphic representations of acceleration. Do you notice some peculiar symmetry here? Yesterday, we started off with the very, very basic velocity, average velocity problems, and then we talked about graphic representations of average velocity. Now we did the very basic average acceleration problems, and we're going to talk about graphic interpretations of acceleration. This is important, and this is so important that I'm going to have you do pretty much an entire lab over this. You do a second lab in Chapter 2. You really have to get this, and you will get this. It's not a hard concept, but I want you to have it so well that you can do it backwards, forwards in your sleep at 2 a.m. You can create a graph that will show you your acceleration almost instantly. When you graph velocity against time, so a couple days ago, or whenever that was, we talked about graphing position versus time, and the slope of a position-time graph gives you what? Gives you velocity. Because if we look at the formula for velocity, change in velocity, or change in position over change in time is velocity. Well, with acceleration, of course, average acceleration is equal to the delta v over delta t. So what's going to be your x-axis? Time, always time. Time marches on independently, doesn't care about you. It just keeps going. You will understand the older you get how deeply, deeply true that is. When you graph velocity versus time, acceleration is the slope. That's easy. So let me ask you a couple questions then. I'm going to get rid of my slide. Of course, when you're making a graph, you're always going to label your axes, and you're always going to label the units on the axes. I know that about you, because you're just those kind of people. So if I have a velocity time graph that looks like this, at your tables, I want you to discuss what you can determine about the acceleration of this object from that line. Go. Okay, I heard the word constant at several islands. I heard people saying things like, well, its rate of acceleration is constant. That's true. As best I could draw the line. The line is not perfect. But with a few minor foibles, this thing is accelerating at a constant rate. It is changing its velocity. We are in the first quadrant, so we assume that these are positive velocities. If this is our origin, this is 0. The magnitude of our velocity is increasing as we go up. That's important. And this thing is accelerating at a constant rate. The rate of change in its velocity is constant. This is easy, Moser. Why are you stressing this so hard? Because it's going to get weird in a second, and I just want to give you a good foundation. So we'll do the same thing with this line. Talk amongst yourselves. What can you tell about the velocity or the acceleration of this object from that line? In my spying and my espionage work, I hear words like increasing rate of change. I heard a couple people mention the word exponential. Yeah, it sure does start to look exponential. It's not perfect, but it's a sort of half-hearted, quickie exponential. That the rate of the acceleration gets larger. The slope gets larger. The slope is changing, therefore the acceleration is changing. Anytime the slope is changing, the acceleration is changing. We cannot get an average acceleration that's real meaningful for this line. We can do the same thing that we talked about with instantaneous acceleration by doing slopes of tangent lines. We're not going to do that in here. If this was calc-based physics, we would by taking a derivative of that point. And that would give us, we would take the derivative of the equation for the line, and then plugging in the numbers for that coordinate for that point would give us the slope of the point. That's beyond what we're going to do. So let's look at a couple more here. Nobody said anything about positive or negative. Is the acceleration here positive? How do you know? Well, yes, because it's going up, Moser. Acceleration is given by the what? Acceleration is given by the what? Okay, this is why I can't lead, chants or cheers or anything. Acceleration is given by the slope. 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 I don't know whose failure this is. I feel like we've all failed one another. Okay, acceleration is given by the slope. Is the slope of this, if you keep taking tangent lines along this, we'll throw in a couple of tangent lines, are the slopes of those lines positive? Yes. Then the acceleration is positive. The slope of the line is positive, the acceleration is positive. Okay, cool. Cool, this is easy. I like this. Easy is good. Oops. Okay, you're just going to have to forgive my imperfections. All right, tell me what you can about the acceleration of this object. You can vote with your hands. You can show me the acceleration of this object with a finger vote. Those of you who had me for chemistry know this. 0! The acceleration of this object is 0. It is not accelerating. How can you tell? The slope of the line is 0. The slope of that line is 0. It's a flat line. Okay, barring wibbles and wobbles because I can't draw straight. The slope of that line is supposed to be 0. So that object has zero acceleration. Now, does that object have a non-zero velocity? Yes. Yes, it does. It's okay to be wrong. We learn more when we're wrong in science in general than when we're right. So it is more than okay to be wrong. It's actually not a bad thing to be wrong. And sometimes you'll hear me yell, "Oh, that's a wonderful mistake!" Because they really are sometimes. And I've made a lot of them. How can we tell it has a non-zero velocity? Because look at it's not on origin. It's not, if we look at the magnitude of the velocity, that's given by its position on the y-axis. Okay, this is easy, Moser. Tell me everything you can about the acceleration of this object. Okay, constant or changing? Constant, because the slope of that line is constant. It's a straight line. Positive acceleration or negative acceleration? Negative acceleration. This is simple. So let's look at an object like this. We'll bring them to a stop. Okay, tell one another, describe at your table the acceleration of this object. Go. What I did here in all of that is this is an object that, and obviously, well, here I can extend this line. Okay, starts at zero velocity, increases velocity, has some positive acceleration, has a moment of zero acceleration at the top of that curve, and then begins to have negative acceleration until it goes all the way to zero velocity again. Okay, cool, this is easy. But you can do this pretty easily. If I give you a graph like this and I say, where's acceleration positive, where is it zero, where is it negative? You just did that. And we're just looking at the slope of a segment of line. So, for instance, we can look at segment A to segment B and say that has positive acceleration. C to D has negative acceleration. D to E, pretty much minus foibles in drawing, has zero acceleration, etc. You can do that. Okay. Here's where it gets kind of strange. So, at your tables, talk amongst yourselves. Where is the acceleration positive? Where is the acceleration negative? Go. Okay, so I'm hearing some good conversation. I'm hearing some people trying to give compelling arguments to convince their fellows of how right they are. So I think everybody can agree that from A to B, we are looking at positive acceleration, yes? Nobody disagrees with that. And this little chunk here, I'll make it some other color. 0. You all get that. I mean, it's easy to pick out the zeros here. We can put the zeros in there. Now here's the part that gets a little bit weirder. From C to F. What's that acceleration? But it's okay to be wrong. Oh, I hate that word. But what we would very often colloquially call deceleration up to a point. Here's why. And that was perfect. I should pay you a quarter and Sid a quarter because that's exactly what I want to talk about. So, from C to D, is there anybody here who would argue that that is not negative acceleration? Okay, everybody's on board with negative acceleration there. What about from D to F?
I would venture to say positive, but I feel like
What would you say?
positive.
What's the slope of the line there? Positive or negative?
Negative.
Negative. So what's the acceleration? Negative. Huh? If the slope of the line is negative, the acceleration is negative. Now, okay, everybody can accept that. I can understand that. I got that. Slope of the line positive, acceleration positive, slope of the line negative, acceleration negative. Yay! Let's go to lunch. Oh, I wish. Okay, G to H. That's a no-brainer. Positive slope, positive acceleration, right? Here's the more complicated and more challenging problem, and hence, of course, the more important one. From A to B, is this thing speeding up or slowing down? Okay. Let's change our wording. The magnitude of the velocity is doing what? Increasing. The magnitude of the velocity is increasing. We commonly refer to that as speeding up. Though you're welcome next time you get into a car with your friend to say, hey, can you please increase the magnitude of your velocity? I have said that to drivers ahead of me on the road in the morning. Okay, during this interval, so here we're speeding up. Speed up. Here, in this interval, is the magnitude of the velocity increasing or decreasing? Decreasing. We're slowing down. Speed down. In this interval right here, is the magnitude of the velocity increasing or decreasing? Increasing. Why?
Oh, we're going in reverse.
You're going backwards of your origin point. Yeah, it's positional. It is positional. It depends on position. It's fine. Because all you have to look at, if you trust the numbers, all you have to look at is the fact that the position on the y-axis, the absolute magnitude of that position gets larger. Therefore, the velocity is getting further away from zero. The magnitude of the velocity is increasing. Now, it's increasing in a negative direction, but they have negative acceleration, and they're speeding up. We'll keep talking tomorrow. Have a wonderful day, folks.